What if I told you that a simple arts and crafts project holds the key to some of the biggest problems in tech today? Seriously, we're going to explore how a single, simple twist in a strip of paper, you know it as the Mobius band, is giving us a radically new way to think about everything from data compression to, get this, ethical AI. So let's unravel this simple but totally revolutionary idea. So, our story kicks off back in the 19th century with a German mathematician named August Mobius. He's the one who introduced this really fascinating object, a surface that just seems to defy common sense. And what's wild is that the idea was so in the air that another mathematician, Johann Listing, discovered it at almost the exact same time. This wasn't just some mathematical party trick, it was a start of a whole new way to think about space and shape. And you can actually feel how weird this is for yourself. If you've got a strip of paper nearby, seriously, try this with me. Take the strip, give one end a single half twist, and tape the ends together. Now what you're holding isn't a normal loop. Try to trace the surface with your finger. You'll go from what feels like the inside to the outside and right back to where you started, all without ever lifting your finger. It's got only one side. So, okay, it's a neat trick. But what if that same principle, that twist that merges inside and outside, front and back, could be applied to our digital world? What if it could make our computers faster, our data storage way smaller, and maybe even our AI a little wiser? Well, that's exactly the question we're unpacking today. All right, here's our game plan for connecting the dots. First, we're going to really get a handle on the strange properties of this twist. Then, we'll see how it's providing this incredibly elegant solution to a massive data problem, and how it might even help us build smarter AI. And finally, we'll zoom out and see how this one little idea is forcing us to rethink the fundamental rules of information itself. Okay, let's dive right in with part one. A twist changes everything. We need to get to the heart of what makes this shape so incredibly special. The best way to get it is to compare it with something familiar. A normal loop, like a cylinder, has two sides, right? An inside and an outside. It's got two edges, a top and a bottom. But the Mobius band? It's got just one continuous side and one continuous edge. And here's the absolute key. Its orientation gets flipped. This is what mathematicians call being non-orientable. This is my favorite way to visualize what that flip really means. Imagine a tiny little creature walking along the band. When it walks one full circuit and gets back to where it started, it finds itself mirrored. Its right hand has become its left. It's literally a mirror image of what it was before. This one property, this reversal, is the simple, powerful idea we're about to see pop up in some incredible places. So now let's actually apply this concept. For our second section, the order of data, we're shifting from the physical world to the digital one, where there's this constant war going on between structure and speed. See, in the early days, data was super carefully structured using something called modeling. But then, in the late 2000s, with the rise of the cloud, speed was everything. That old, slow modeling was seen as a bottleneck. The attitude was just get the data in. We'll figure it out later. Well, by the mid-2010s, later arrived, and it was a total mess. And this was the price. Without that structure, data quality was awful, security became a nightmare, and performance tanked. It became almost impossible to get real, trustworthy insights from all the data they'd rushed to collect. So yeah, they had speed, but they totally lost coherence and safety. They really needed a way to get both. And that brings us to section 3, the power of a flip. This is where our little paper loop makes its grand entrance back into the story, offering a surprisingly elegant fix for these really tough engineering problems. Okay, here's the first mind-blowing application. Imagine you have a data signal, right? And it bounces between a positive pattern and a negative one. A normal data compressor would see two totally different patterns and would have to store both of them. But non-orientable compression is smarter. It realizes they're just mirror images of each other. The same pattern, just flipped upside down. So instead of storing two huge patterns, you store just one of them, plus a single tiny bit of information, a flip bit, that says, hey, for this part, use the inverted version. It is so efficient. And the benefit here is crystal clear. Before, you're just wasting tons of space storing redundant, mirrored information. After, you have one main pattern and a tiny bit of metadata. The result? You could see a storage reduction of up to 50%. It's the Mobius idea in action, treating two things that look different as actually being the same thing, just from a flipped perspective. Now, this same idea applies to the actual physical layout of computer chips. A standard network on a chip might be shaped like a torus, a donut. But a flip torus intentionally adds a Mobius-style twist to the connections that wrap around the edges. It deliberately puts in that orientation reversing flip we saw earlier. So why on earth would you do that? Well, the benefits are huge. That one simple twist gets rid of these annoying edge effects in the network. It weeds out certain types of problematic data. It helps stabilize network traffic, and it actually simplifies the whole model. It's this same simple trick, a flip, that leads to a massive performance boost.
Okay, so we've taken this concept from optimizing concrete things like data and computer networks to its most profound and challenging arena yet. Section 4, Twisted Logic in AI. Can this same geometric idea help us tackle one of the biggest challenges of our time, building safe, aligned, and truly ethical artificial intelligence?
A pretty new research program called Geometric Ethics is proposing a radical shift. They're saying instead of trying to write an endless list of rules for an AI to follow, what they call behavioral specification, we should focus on the architectural design of the AI's reasoning process itself. At the core of this is something called the Riemann-Seam hypothesis. Now, I know, big words, but stick with me. The idea is that we can map out ethical choices on a geometric landscape. And on this map, deep conflicts between value systems, like choosing the greatest good for the most people versus sticking to a strict moral rule, they don't just create a fork in the road. They create a seam, a topological twist, exactly like the one in our Mobius band. It's like a fault line in the landscape of logic, where two totally different value systems meet and warp the very ground the problem stands on. So this perfectly frames that classic dilemma. When an AI hits one of these impossible choices, where any decision violates some deeply held value, what is it supposed to do? And here is the paradigm-shifting answer they propose. The goal isn't for the AI to pick a side. The goal is to design an AI that can navigate the twist itself. It's about finding the wisest path through the conflict by recognizing that the seam between values is a fundamental feature of our world, not some bug you can just program away. Okay, so we've seen how a flip can optimize our data and maybe even reframe ethics. But how do you even find these flips, these twists and seams, when they're hidden in a massive ocean of data? Well, that's where we zoom out in Section 5, the shape of information, to a field that's dedicated to exactly that challenge. This field is called topological data analysis, or TDA. It has a really cool workflow. You start with just a cloud of raw data points. Then the algorithm starts connecting nearby points to form shapes, and it does this over and over at different distance scales. As it does this, it tracks the important features, like loops or holes that appear and disappear. The result is a kind of summary of the data's essential shape. And that summary often looks like a barcode. The logic behind it is simple but really powerful. Long bars represent features that stick around across many different scales. These are the true shapes in your data, the meaningful twists and loops. The short bars are features that just pop in and out of existence really quickly. They're probably just noise. So TDA is basically a way to find the real, persistent shape hidden in all the chaos. And this brings us to our conclusion, Section 6, Rethinking the Rules. We've gone all the way from a simple paper strip to the fundamental shape of data, and it's all been connected by one incredibly powerful idea. This quote from that geometric ethics paper just captures the whole shift in perspective perfectly. True wisdom, whether it's in a human or an AI, might not be about just picking the right answer from a list. It might actually be about the quality and the structure of the space where the reasoning happens, a space that's flexible, coherent, and able to navigate the twists and seams of a very complex reality. So in the end, a simple geometric twist has opened up totally new frontiers in computing, in data science, and in AI. It proves that sometimes the most profound innovations come from questioning our most basic assumptions. It really makes you ask, what other fundamental rules that we take for granted are we ready to flip?